Now, if you really want your notes to be helpful, you will not endeavor to write down the things I write down. They're already going to be there. You should be endeavoring to write down the things that tell you why I'm doing what I'm doing. Because that's what's missing from your notes. I tutored for a solid all of lunch, and I tutored yesterday after school for about 20 minutes. When I look at your notes, and I don't check them on purpose, you just happen to have them out, you are meticulously writing down the things I write down, believing that that's going to help you. And it really won't. Have you ever noticed how I tend to repeat myself, but also start like saying something that has nothing related to the problem for a few moments? That's so that those of you who are still finishing writing your notes can write your notes out. What you should be trying to do is write down the reason why I'm making the choices I'm making. It will help you far better than what I'm writing down. So I know that's hard, which is why I wait for your feedback before I go on. But if nobody's moving their pencils, I just keep going. Does that make sense? So here, I'm just going to follow along with what this was. They said the box was going to move up the ramp at a constant velocity. I know this is the last step in that four-step process, but I'm just going to throw it down there. It's got to be net force equals 0. In addition to that, the box doesn't go up the ramp unless somebody pushes on it. So there's got to be a force this way. Somebody's providing it. Now, that being said, the first thing I think you should do is draw a free body diagram, which, you've heard me say this a lot. And drawing a free body diagram, I believe neatness counts. You've heard me say that a lot. But most importantly, I believe that you should draw one large enough so that you can successfully use it to navigate the problem. So I start with the weight, and I tend to make the weight kind of my guiding size. I know ultimately that it's going to determine how big the other arrows should be. Now, if you don't understand why that's true, consider for a moment that I'm going to eventually draw a coordinate system. Now, I tell you to draw the coordinate system after you've drawn all your forces in. But look, we've done the inclined plane problem a couple of times already. It should make sense that we're eventually going to draw a coordinate system like that, where this is the ramp. The reason I bring that up is this is how much of that force is aimed down the ramp. Now, if you don't understand what I just did, the weight's at an angle compared to the ramp. All I did was kind of figure out how much of this red force, there's a part of it that's going to be this way and a part that's going to be this way. If I want to know how much is in each direction, I'm looking at, in math terms, we'd call this the projection. But we're looking at how much of this is projected along the axis. So I drew a perpendicular line to the axis to let me know that this is about the size of the force along the axis. Now I'm going to get all that out of the way. But I did that because the guy who's pushing up the ramp has got to push at least that amount up the ramp to balance what's going down the ramp. Now I can do this because I've done this from experience before, and I'm hoping you see now kind of how I'm dealing with the sizes of these. Let's look at the other direction. I don't know what I just did, but there's definitely a y direction to this problem. If I look at the projection here, that suggests that the amount of weight into the ramp has to be that big. I know the object doesn't sink into the ramp, so I'm going to draw a normal force that is about that size. Now, none of this discussion really determines whether you can solve the problem or not. This discussion is just about trying to get out a reasonable diagram that reflects the forces acting in this system. That's how I kind of determine the size of the arrows that I draw. Now, you might not be able to do that, but you certainly can be careful in your diagram. And I would encourage you to try to be careful. Now, we've drawn all the forces acting on the box, and I'm purposefully being very slow and deliberate so that you guys can be writing yourselves some instructions as we go. But from this point, I have my coordinate system. I need to break up the weight. And the first reminder I need to throw out there is that this is the 25 degrees. It's always going to be between the weight and the axis that has the normal force. I've been calling this the y-axis every time, but this is the axis where the normal force is. That one gets to 25 degrees. Now, I saw this all day yesterday after you guys left. People not knowing what to do next. First, there's plenty of people who still think this is 25 degrees. And I'm not going to spend a lot of time trying to convince you you're wrong. You're wrong. Just memorize this for now. If you need convincing, I can convince you using a reasonable argument. But let's not do that right now. Let's make that a separate conversation. On the other hand, I also have people who, when they go to draw in their components, are really doing it wrong. Your component has to get you from the starting point here to the ending point here. You're drawing a triangle. And I said to wrap that triangle around the angle. And some of you are doing a masterful job of screwing this up. With many people drawing something that looks like this. That's a right triangle, and it is drawn around the angle. And it is completely wrong. And the reason is because of where the right angle is. Component vectors are perpendicular to each other. I don't know if that's in your notes or not, but it really needs to be. If you're drawing components, those vectors have to contain the right angle. The red one here is the resultant. It's got to be the hypotenuse. The white ones have to be the legs of the triangle. They have to be at a right angle. So there and there is where my right angle should be between the components. Otherwise, you'll get the sides labeled wrong. Worse, you'll get like a tangent in there if you're not real careful. And when you're breaking something into components, you'll never use tangent. It's going to be side for opposite and cosine for adjacent. Which is also why I've recommended, just in the back of your mind, if you want to save some time, the one that's lined up with the normal is probably going to be the one that's based on cosine. I do say probably because, every problem's a little different. But for an inclined plane, when you're just learning, I would encourage you to just see that these problems all have some similarities to them and use those similarities to your advantage right now. Now, this picture's gotten to me to be awfully complicated looking. Maybe not to all of you, but to me it's a little complicated looking. So if you don't mind, I'm going to simplify it, okay? I guess it really doesn't matter whether you mind or not, because I'm probably going to do it anyways. guess that red guy's going to stay there. I just want to draw the white one up there and write that as W sine theta. There we go. So what I see are 4 forces, 2 in the x direction and 2 in the y direction. Now, in the first part of the problem, we're told net force equals 0. And they want to know, how hard do I have to push the box? So although there's more to do here, and if you follow all the steps I've given, you'll know that you should break this up into the x direction and the y direction and evaluate them separately. But if all they want is this, and it only is in the x direction, I'm only going to worry about the x direction. F push minus weight sine theta equals 0. Now, all they want was the size of the pushing force, which means F push equals weight times the sine of theta. Now, yeah, there's a numerical answer there, and I know that that's important to you guys to get the number right, but to me, this is the answer. Maybe one extra step, replacing weight with mg, but to me, this is where it ends. Because now we have solved this for any problem where you're pushing something up the ramp. You just need the angle and the weight. But you guys like to have the answer. So I don't remember what the mass is. 15? 50. So 50 times 10 times the sine of 25 degrees. And there's your answer. Is it 211?
Yeah.
Acceleration of gravity is 10. So I have to multiply by the acceleration of gravity. You can use 9.8 if you wish, but for problems like this, I'm going to use 10. If you don't multiply by g, you're not actually getting a weight. You're getting, I'm not sure what. But it has to be in units of kilograms, meters per second squared to be a force. So 50 is in kilograms, 10 is in meters per second squared. The weight is mg, mass times the acceleration of gravity. It's not negative because direction was already handled here. So, still 211, right?
Yeah.
So 211 newtons. Now, they do this problem over again, and you might think it's a whole new problem, which is why it took you an hour to do the homework last night, but they tell you that instead it accelerates up the ramp. Is that right? It accelerates at 1 meter per second squared up the ramp. Let's consider how this is different. It means that the net force is equal to ma, because it accelerates. But we purposely chose up the ramp to be the x direction. So the only thing I have to change in all the work that I did is that this in the x direction is no longer 0. So get rid of the solution that deals with 0, and instead write net force equals ma. So F push is going to be ma plus mg sine theta. Again, to me, that's the answer. But if you want a number, it'll be 50 times 1 plus 50 times 10 sine 25 degrees. Because the acceleration, this is still the 50 times 10. That's still the weight. But this A represents the acceleration they gave us in the problem, 1 meter per second squared. They tell us the acceleration, which makes this 261 newtons. And if I wanted to accelerate, I got to push harder. How much harder? Well, it depends on how much it weighs. If it were a heavier box, I'd have to push even harder than that. But basically, I have to push with this force just to keep it from sliding back down. Now that force will also push it up at a constant velocity, But if I want to accelerate it, I need to push harder. The 10 meters was a distraction. Were you distracted? If so, good. Don't be distracted on the next one. All right. Let's just talk about the ramp problem. There's no friction, right? That was put out there first. And so problem number 1, problem number 7, both start with no friction. That's kind of the implied idea. So I have a ramp. Its angle is theta. And I just plop something on there. Okay, if something's on a ramp, if there's no friction, it's going to slide down the ramp. Not a surprise, right? Now, instead of redrawing everything, you do realize that we're talking about just two forces now acting on the object, normal and weight, which I'll just write as mg. And I'm going a little faster this time because these are all the exact same steps as before. I will find after doing all of the same steps that there's a component of the force in this direction that I'll call mg cosine theta. And there's a component of the force in this direction which I'll call mg sine theta. It'll be all the exact same steps to get right back here. So can I just say that we know those are going to be there for a ramp? Or do you want me to go back through the free body diagram and everything? Because I think this is okay, but if you want to, I'll do the free body diagram. Raise your hand if you want to see the free body diagram. Oh, thank goodness. So, and this is really, I don't want you to become complacent. AP will give us weird stuff. But I want you to nail this too at the same time. So consider that this looks to me to be unbalanced. Meaning, if you don't have something pushing you up the ramp, you will slide back down to the bottom. Does that seem like a not an unreasonable idea? So, if you figure a Hot Wheel car, if you don't hold it onto a ramp, it will roll to the bottom. So, does this look unbalanced to you as if it would roll to the bottom? So, net force equals ma. Now, is downwards towards the bottom of the ramp going to be positive or negative in your mind right now? Which one do you want it to be, positive or negative? So you want this way to be negative x. Is that okay? Done. So that also means then that this way is positive x. Well, if I want the acceleration, and there's only one force, it's going to have to be negative mg sine theta equals ma. Those are the only forces acting in the x direction where there's an acceleration. In the y direction, the net force will be 0 because every time I've stood on a ramp, I've stayed firmly on the ramp. I don't sink into it. So I think it's balanced up and down. So I hope that you're seeing the thing I see, that the mass doesn't matter here. It cancels out, leaving me with the acceleration down the ramp is g sine theta. And before you ask where'd the negative sign go, I said the words down the ramp, because that's what the negative sign meant. That's the acceleration down the ramp. Now keep in mind, I'm not throwing away the information that I'm putting out there. I'm saying that this acceleration is down the ramp. Now, this answers all of question 1 and part of question 7. Question 1 asked, what was the acceleration of a boy on a ramp angled 40 degrees? G is 10. And it's sine of 40 degrees. The 10 is in meters per second squared, so I don't know what the answer here is. It's going to be like a little more than 5, right? Actually, probably a lot more than 5. 6 something? 6.4. 6.4 meters per second squared. That's the acceleration down the ramp. Now, look, You guys probably don't have an appreciation for this, but sine of any angle is going to be between 0 and 1. Right? You do know that part, right? The sine of 90 is 1, sine of 0 is 0. I know you don't like this, but any number between 0 and 1 is a decimal, which means that sine is a percentage. It's a part. It's how much gravity do you have to work or do you get from your ramp. That's really what it is. It can't ever be more than 10. The acceleration can't be more than 10. It can only be 10 if you have an angle of 90 degrees. Right? Because then your ramp is just you hanging onto the side of a wall. Yeah, you'd fall at G. But also, if it's flat and level, what would your acceleration be? Yeah, you wouldn't go anywhere. It's not a ramp. It's the floor. So let's talk about question 7, because this is the same for question 7. What was the angle on question 7? 30 degrees? So the angle on question 7 is 30 degrees, which means that the acceleration is 5 meters per second squared down the ramp. Because sine of 30 is 0.5 times 10 is 5. Now, here's the question. What does this mean? For the problem, they asked something about how fast is the car going. Well, they want the car to go up a distance of 1.5 meters with some initial velocity that is unknown but will eventually come to a stop when it's 1.5 meters above where it started. And if up the ramp is positive, then down the ramp has to be negative. Do you now see what you're going to have to do here? Two-part problem. Forces can only tell you acceleration or a force. That doesn't mean that that's the only thing you're going to do with that information. So although I've said this a couple times, it probably didn't sink in that Newton's laws can only tell you acceleration. That's it. They can also tell you a force, but that's it. That doesn't mean that that's where it ends. You can use it. So I'm going to think V final squared minus V initial squared equals 2a delta x. So 0 minus Vi squared equals 2 times negative 5 times 1.5. It says it goes 1.5 meters up the ramp. Right? I'm pulling it from memory though, so if it's a different number, let me know. But doesn't it say it goes, you want it to go up 1.5 meters? All right. Well, that's it. That's all. This will be how fast I have to push the car. The right side is going to be 150. No. 15. Duh. So square root of 15? Just a little less than 4, right? 3 point what?
3.87.
And it's positive. I have to push it up the ramp for it to go up the ramp. Yay. One step. The weight down the ramp, mg sine theta. What's holding it in place? The rope. Right? That's what has to be balanced. So how much can the rope hold? What's the mass of the box? 30. I didn't draw any pictures, but if the gravity pulls down the ramp at mg sine theta, and the rope is pulling up the ramp with t, if I don't want it to go anywhere, they have to be balanced. If I want to find what angle I can get to, it's there. All right, I know you guys have to go.